Hi. In this unit, we're going to start talking about AlphaGo and AlphaZero, and there's going to be quite a few units in this section. This is getting to be old news now. So this is 5 years ago, October 2015. AlphaGo defeated the European Go champion. This was a big event, but it wasn't yet the world champion. And then in March, just a few months later, AlphaGo defeats Lee Sedol. And Lee Sedol was considered the preeminent Go player in the world. And there's a great documentary on this you can get on YouTube. It's very poignant. Poor Lee Sedol really was not ready to face the possibility that there were superhuman Go programs. Go had always been something that computers could not approach. AlphaGo Lee, this is the program that defeated Lee, is trained on both human games and self-play. It's trained for months, and then in the match, it's run on many machines with 48 tensor processing units, TPUs. Now, the next step, this is about a year later, is called AlphaGo Zero. AlphaGo Zero stops using books of games, human games to train on. It trains entirely on self-play, playing itself, starting with nothing but the rules of the game. And it's trained for only 3 days. And in matches, it's run on one machine with 4 TPUs. So it's trains faster, starting with just the rules. And it defeated AlphaGo Lee, the earlier program running at its full strength under match conditions, 100 games to 0. So this was a huge advance over AlphaGo Lee. And then AlphaZero, December 2017, so now this is 3 years ago. Again, this is all sort of old news. AlphaZero defeats the world's leading chess computer program, because since about 2000, computer programs were superhuman in chess. So the strongest chess players have been computers for quite a while. But AlphaZero defeats the strongest previous chess computer. And this is fascinating, and we'll get into this in more detail in later units. The general algorithm for AlphaZero is it's essentially the same as AlphaGo Zero. They just changed the rules. And since the learning algorithm is just starting with the rules, it has a definition of what a legal move on the board is. It's essentially the same program. So the same program is now superhuman in Go and chess through self-play using nothing but the rules. Okay, so this is a shocking development. I think we're still trying to understand the significance, but I'm going to start in this unit with background. What happened in computer game playing before AlphaGo. So early computer chess. The first computer chess algorithm is Claude Shannon, 1949. And then that was greatly improved by something called alpha-beta pruning, which many people came up with, including John McCarthy, circa 1960, about 10 years later. And alpha-beta pruning was the backbone of all computer chess programs, including Stockfish, the one that AlphaGo, that AlphaZero defeated up until AlphaZero. But for a long time, throughout the history of chess programming, Go was considered not approachable by these methods. So the branching factor in Go is so much larger, and you have to sort of think so much further ahead that it just was not approachable. In 1993, there was the first significant advance in computer Go, and that was based on Monte Carlo tree search. And the basic idea here is that when you want to you've got a set of possible moves you can make. When you want to determine which one of those moves is better, you evaluate each one. And the way you evaluate a move is to compute what's called a rollout. You have some fast policy for picking moves, and you just play a game out to the end, and you see who wins. And you do that again and again with your with a kind of, you put stochasticity, randomness into the play of the game. You do it again and again, and you see how many times one player versus the other wins under those rollouts. and then you use that as your board evaluator to pick your move. And that was a significant advance in Go. You know, Go could play at some intermediate beginner level. Go programs could play. Now, there's an independent line of research going on that's going to be very relevant in the development of AlphaZero, which is the Bandit Problems. So this was Robbins' 1952 formulated Bandit Problems. So the idea here is we have a set of choices that we have to pick from. Now, we're ultimately going to think about moves in a game like Go, the choices we have to pick from. But in the original formulation, it was the primary example was a casino with slot machines. And a slot machine was known at that time as a one-armed bandit. And the technical mathematical problem was you're in a casino, you've got a bunch of bandits. Each bandit has an expected payout, but some of them have better expected payouts than others. And let's suppose these bandits are bad, so they actually have, you know, there's various payouts for each bandit. And you get to play each bandit, and you have to figure out which bandit has the best payoff, but the payoffs are random. So you have to you're faced with this exploration and exploitation trade-off. You have to figure out which machine is best and then play that machine most often. I think I've said all of this, but it's on the slides. So there's an algorithm for this developed in 1985. So we're getting somewhat more recent, called the upper confidence bound algorithm. So if I look at one of my bandits and I play it some number of times, I get a bunch of random payoffs. And what I'm interested in understanding is the actual expected payoff. I'm assuming that each time I pull the arm, I'm getting an independent payoff. And so I can use sort of a classical confidence interval. The true payoff of an arm A, of an action A, is what I measure over n draws, plus or minus twice the standard deviation of the, this is sort of a standard 95% confidence interval for the mean of a random variable when you're measuring it a bunch of times. It's the measured mean plus or minus twice the standard deviation divided by the square root of the number of times you pull the handle. And as you pull the handle more, this confidence interval gets tighter. So the more you play a machine, the tighter that confidence interval gets. Now, the algorithm, the upper confidence bound algorithm, says for each machine, I've got a confidence interval because I've played that machine some number of times. So what I do is I pick the machine where the confidence interval has the largest upper value, the machine whose possible payoffs is as large as possible. So you take the confidence interval, you take the upper bound of the confidence interval, you take the machine with the largest upper bound, upper confidence bound algorithm. And you can prove theorems about this. So how rapidly or how much reward you get over time under this algorithm, because it is an exploitation trade-off algorithm. This algorithm was applied to game tree search for Go in 2006 and 2007. Silver is one of the developers of AlphaGo, so this is earlier work. And so now we're going to be working with a search tree, a real game, a search tree. And what we're going to do is at each node of that search tree, we've got a set of choices. Well, let me back up. I'm trying to pick a move at a position. And what I'm going to do is grow a search tree. And the way I grow the search tree is by taking a given search tree, initially it's empty, and I'm going to do a set of simulations. And each simulation is going to pick a descent down that search tree and then expand a leaf where it reaches in that descent. So that's a simulation. And that simulation has to pick a move at each node of the search tree as it's going down. So that choice of a move at each node of the search tree as it's going down, and so you're just going to go down and expand the leaf, is made using the upper confidence bound algorithm. So at each node that you reach, you look at the children to choose from, and you have a confidence bound at each child, and you use the upper confidence bound algorithm to pick which child to go to. Now the two players are playing against each other, so they're always picking the best possible move for the player to move. So this upper confidence bound is then applied to selecting moves as you descend in a search tree, and it's used at each choice, and then you expand the leaf you reach, you construct all of its choices, and you also back up a value from that leaf to the root. And as you back up that value, you're getting a new value at each node. You're increasing the number of trials of each node on the path you descended through. We'll go through that in more detail in the next unit, because that is basically the AlphaZero algorithm. And there are a lot of details that I just sloughed over. So I'm going to go through that in a lot more detail in the next unit. So another idea, 2009, is bootstrapping from game tree search. So this was written in the context of chess algorithms. And in chess algorithms, you're doing min-max search, certainly in 2009, you're doing min-max search with alpha-beta pruning. And so for a given position S in the chess game, you can compute a min-max value, a min-max score for S by running this chess algorithm, min-max search with alpha-beta pruning. And then what you want to do is train a value function. So in chess, people talk about the static board evaluator. When you reach a leaf node in chess, there's a function you call that assigns that leaf node a score, who's ahead and by how much, the static board evaluator. And if your static board evaluator was a neural network, we want to train it. So we want to train the neural network to match the min-max value. So if you can do this is a kind of Bellman error. We want to minimize the Bellman error between our static value and our min-max value. So we're training the static valuator to match the min-max value, where the min-max value is using that static evaluator at the leaves. And this is called tree search bootstrapping, right? You're training the static evaluator to be more like the min-max search algorithm. And if you could do this exactly, then you're essentially doubling the depth, because if I could train this to be exactly this, then if I use this as a static board evaluator, it's that the static board evaluator is giving you the power of that tree search. And this idea of tree search bootstrapping is also sort of fundamentally part of the AlphaZero algorithm. So next time we're going to go into the details of the AlphaZero algorithm. Thank you.